Inductance describes a process by which when a current starts or stops, it creates a magnetic field, and then that magnetic field affects the current that just started or stopped. So we're going full like head spinning in a circle here with today's video.
But before we get to AC, we want to talk about, hey, guess what? The symmetry of magnetic and electric fields. It's pretty exciting stuff. Um, and we talked a little bit about the sort of incestuousness of it, right? That a moving charge creates a magnetic field, and the changing magnetic field creates an electric field. One of the results of that is something that's called self-inductance. Um, what is self-inductance? Well, you start a new current, right? I connect a circuit. The changing current creates a magnetic field. The changing magnetic field creates an electrical field. And just like we saw when we were pushing a magnet through the wire loop and the magnetic field opposed, in this case, the electric field opposes the initial current. Now, most of the time that effect is pretty small and lasts short, but we can build things that make it more significant. And if we have a device that has a significant self-inductance, we call it an inductor. And its inductance is defined this way. The voltage created by the inductance is equal, or the inductor is equal to its inductance L, multiplied by the change in current over time, right? So notice this isn't just the size of the current, it's how fast the current is changing. So why do you want to do that? Why would you want to have something that actually opposed what you were doing? You were trying to start a current, and it's making it harder to start the current. Well, there are a couple reasons. One is that a large inductor can produce a really large EMF, and even one that's bigger than your original EMF. So I might have a circuit with a 12-volt battery. I can actually create an EMF much larger than 12 volts with an inductor. And so let's do that math here quick to just sort of see that that's true. If I have a large inductor in 120 volt current, and I suddenly send in a 10 amp current in a thousandth of a second, or here I'm talking about cutting it off, then what happens? Well, throw those numbers into our equation for an inductor, and you see that I get a 10,000 volt EMF out of a 120 volt circuit. So that's a really massive voltage. And these are some big numbers here too. That's a large inductor. That's a pretty large voltage, but still, that's pretty huge. So what purpose does that serve? Well, let's look at an actual circuit. If I flip these down to this first position when it's going through the battery, the inductor gets charged. What does that mean? Well, it just means that basically it initially resists when I turn it on, and after a while it's not resisting it anymore. It's got a current going through it. If I switch those switch all at the same time, then the current through L changes really quickly. Okay, that means it's creating a voltage. And let's look at the circuit. It creates a voltage that's going to go onto this capacitor. Okay, so it's going to throw a bunch of charges onto one side of this capacitor and polarize and charge this capacitor at a much higher voltage than I could down here, right? Remember we said that we can create a really high voltage here. Well, if I switch that on and off, it's not going to send a bunch of charge there because it doesn't hold a lot of charge, but it'll do it at a high voltage. If I switch this on and off and keep doing it, that higher voltage is going to allow me to charge that capacitor to a much higher level than if I just had the battery alone. And that, as you might remember from talking about capacitors, if I want to make this flash work, then I connect this to my flash suddenly, and it can discharge that capacitance really quickly. So that's one of the main uses of an inductor like this. Now, we also need to talk about what happens when we throw a resistor into the circuit. Um, in this case, it's going to change the way that the current, that the inductor resists the current, right? So when I turn this battery on, when I hook it up to 1, the inductor is going to resist that current, right? Um, like a capacitor, this RL circuit has a time constant, so it's going to initially stop the current from happening, but then it's going to slowly allow that current to build up to what you would normally think of if that inductor wasn't there, right? So if we have a certain voltage and a certain resistance, we're going to have a settled current, which is called I naught here, and it's only going to gradually get up to that current. So that would be a use for one of these circuits. This tau down here, just as we saw with a capacitor, is defined by the inductance and also by the size of that resistor. And we can calculate the current at any time. And that's what this curve here is. It's actually this equation. So when this is 0, e to the 0 is 1, and our current is 0. As time gets bigger and bigger, this number gets larger, negative larger, which means this value gets closer and closer to 0. And so you get this curve that moves from 0 to I naught. After some time, after you turn it on, the current is going to settle, right? And be at I naught, and the inductor is no longer opposing the circuit or the current. And then I might wonder how much energy I've got stored in that inductor. We can calculate that. Has to do with the size of I naught, right, and the size of the inductor. And then when I switch the current off, right, so I just have an R and the L in the circuit, that inductor is going to discharge, right, and its immediate response is going to be, it's going to keep that current going, right, because I've got a current moving through here, let's say left to right. It's going to, when it stops, it's going to resist the stopping, so sort of a double negative, and it's going to continue that current moving in the same direction, but then that current is going to slowly diminish, right? In the same with regard to the same inductance, right? The same tau value, and eventually, right? There's going to be no current here because there's no permanent voltage. There's just the voltage provided by our